for MLB pitchers, there is something called Tommy John surgery. It's if you have a torn UCL or fatigued UCL, you have to get this Tommy John surgery, and it is said that people who go through Tommy John surgery actually pitch faster after the surgery. I read some article on whether this is true or not, but it seems like what's really happening is that just before the Tommy John surgery, the pitchers are already very fatigued, so they will be underperforming, and after this corrective surgery, they will be pretty much back to the normal. So that's why it looks like their speed is improved. But anyways, well, whatever that is, this question is listing the miles per hour of their average fast full speed before the surgery, the season before the surgery, and the season after the surgery. So they're comparing them. And the question is, test the hypothesis that pitcher's fast full speed increases after Tommy John surgery. All right. What type of testing is this?
List testing.
We have in my actual problem, I put the pitcher's name here, right? So it's the same picture before and after. If you have a same person or same entity that produces the data before and after, or under some different conditions, what kind of data is it? It's called a paired data, okay? It's a paired data. So here, this is a paired t-test. It's a paired t-test. And what you're doing is you're assuming that the difference between before and after is pretty much like a normal distribution. Okay? And in many cases, it's not so, it's not a far-fetched assumption. It's like, usually you would see that difference between two things would be something symmetric, and it's harder to be very different, so it's somewhat like a bell curve. So you would think that the t-test would be appropriate. Okay? All right, so what do we do? Well, so you have to help me out here. So what you want to do is you want to go to list 1 and type these numbers in. So 2, -1, 1, 0, -2, 4, 2, 0, 1. Okay? Now, sometimes I might not give you this. If it's not given, you actually have to write them down, okay? So 2 difference would be this minus this, or you can do this minus that. The meaning will change. So, but you have to be consistent. If you want to write b minus a, you have to be consistent for everything. If you want to do a minus b, you have to be consistent for everything. So it's this one will be -1. This minus this is +1. This will be 0. This is -2, 4, 2, and then 0, and then 1 and negative. Okay, so I think. Okay, so type those numbers in, and what I want you to do is to go to one variable. So click stat and do one variable statistics. Okay, and then I'm going to ask you for the numbers a little later, but because this is hypothesis testing, we're going to do 4 steps. Okay, so step 1, what do we do?
Hypothesis.
Yeah, hypothesis. What's the null hypothesis?
That they're equal.
They're equal, right? Okay. So I would say
that it doesn't increase?
Yeah, that it doesn't increase. So let's say x is the average pitch speed before, and then y is the x1 is the average speed before, and x2 is the after. Okay, and we want to say that they're equal. Now, you can also state this by using d, which is the difference. Difference d is, you can define it as x2 minus x1, or x1 minus x2. That's up to you. Okay. And we're saying that d is 0. Okay, so that's one thing. And now, what are you trying to prove? You're trying to prove that x2 is actually bigger than x1. So
Greater than.
yeah, x2 would be greater than x1 bar, which would mean that you want to prove that since we're defining d as x2 minus x1, this would be that d is greater than 0. That's the alternative. Okay. And since we're just going to work with d, it's just the regular t-test on d. That's all it is. Okay. So step 2, we have to find the rejection region. And because we're using t-distribution, we need the degrees of freedom. What's the degrees of freedom?
5.
No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pictures. So what is it?
9.
9, because degrees of freedom is n minus 1. It's 9. And I didn't state the significance level here, but let's just say alpha is 0.05. I keep forgetting. I actually should write this. Oh, another thing is that there's something I didn't write down, which is that assume that the difference follows an approximately normal distribution. Okay, because that's the condition that t-test would work. I'm saying this because after the next exam, for the final exam, we're going to talk about non-parametric tests, and that one can be applied even if the distribution is not approximately normal. So, yeah. So, yeah, I'll explain that once we get to the non-parametric test. But anyways, since this is d greater than 0, what kind of test is it? Right tail, left tail, two tail, which one?
Right there?
Right tail. Right. So that means we need to do inverse t of 0.95, because or 1 minus 0.05 with degrees of freedom 9. Can somebody give me the value for this?
1.833.
Oh, really? 1.833? Okay. Oh, all right. All right, so that's 1.833. So 1.833 is going to be our rejection region. Okay, what's the test statistic? That's when I need you to give me the one variable stat. Okay, so from the one variable stat, what's the average value of the difference? I mean, over there.
0.6.
0. What?
0.6.
6. Okay. And what's the standard deviation, the decimal correctly?
1.7763.
Okay. And therefore, since our hypothesis, null hypothesis says that d should be 0, but in our sample d is 0.6, we have to do 0.6 minus 0. You want to look at the difference and divide it by the standard deviation, 1.776 over square root of 10. Okay? So this is like, I mean, you can first calculate this and divide from 0.6. 2.2, 6, it will still be less than 1.
1.06.
Really? It's bigger than 1?
Yeah. 0.6 divided by 1.776 divided by 10, square root of 10, I give 1.6. Anyone want to check me in?
That's right, okay. Yeah, the thing is, you really want to parentheses around here, okay? Okay, so, does this lie in the rejection region?
No.
No. So, outside the rejection region, so
We don't
in
have,
step 4, what do you say?
we do not reject.
We
We
do
don't-
not have enough evidence to reject the null, okay? So, or we can just say we fail to reject H0 because it's outside the rejection region. Okay. So then you have to write down something like we do not have enough evidence to show that Tommy John surgery increases the fastball average. I'm not going to write everything, but you know what? So that's what it is. Now, what if the people who researched this topic really believed this, and then they just looked at some more historical figures? This was like just from last season, but maybe they wanted to find out something like 300 pitchers, okay? And they did this, and if it turns out that these values are still comparable, what do you think will happen with 300?
Then they actually might say the Tommy John surgery will help.
Will improve the speed, and what's the difference if I have more people? Where does that 300 go? Right here, right?
Yeah.
Well, it'll also change this one as well, because degrees of freedom will
Yeah.
be bigger, and then this value will be decreased, okay? Somewhat, not much. But this makes, because it's a denominator of the denominator, it's actually like the numerator, so that's going to increase this value by a lot, okay? And in that case, you'll be able to prove. Which means that there are some cases when you have a small sample, you don't have enough strong evidence to justify it from small sample, but if you have a big sample, then you can see the effect that's significant. Right? They kind of looked at the recent sample of 43 athletes, looked at their GPA, it's 2.91. Okay, that's not bad, that's good. Right? And you know, if you in some big schools, they really get money from the athletics department. Their college basketball teams and football teams, they do earn money. So what do they do with the money? They would hire extra tutors just to make sure that they can do well, because if their GPAs go down, they can't play. So it's an important thing. So yeah, so they'll track something like this. So they got 2.91, standard deviation 0.23. And then they also noticed that when they kind of sampled 101 non-athletes, their average GPA was 2.81, and the standard deviation of the grading point average was 0.31. So the athletics department is quite excited. Hey, 0.1, that's a significant difference, I think. They want to actually prove that it is. So we should look at this question. So can the athletic department claim that the average GPAs of its athletes are higher than that of non-athletes? Can you do that? what type of testing is this? It's two samples, right? So it's the large sample, two sample test. Okay? So it's a large two sample test, and there's also something you can do with small two samples, but that's more complicated and it's not very desirable. So that one we didn't cover in the class. Okay. All right. So it's the large one, which actually justifies that we can just use the normal distribution. If it's big enough, we can just use the normal distribution. All right, so we are just going to use the normal distribution. Before we do that, we need to have a standard deviation of the combined thing. So if you assume that there is really no difference between these two groups and they come from the same population, then we can think about the standard deviation that's combined. And the formula for that is square root of S1 squared over N1 is S2 squared over N2. All right, so can somebody do this calculation and tell me what you get? So you need to do 0.23 divided by N1, which is 43, or 0.23 squared, plus 0.31 squared over 1.
0.0467.
0.0467. Okay. Now this really is the standard deviation of the average D. So there's no need to divide. You've already divided by the square root of n here. So when you put in the formula for the test statistic, you shouldn't be dividing by square root of n. Okay. So don't do that. Okay. So here we are doing comparison of mean or hypothesis testing of mean of two large independent samples. And it's this large that allows us to use the normal distribution, okay? All right, so step one, what do we do? H0, X1 average, and X2 average are the same, right? H1. We're talking about this is X1, so we want to show that X1 is bigger than X2. Now, as before, we're going to talk about this as differences. Okay. Yeah, and you can choose the difference to be this minus this or this minus this. You can choose whatever, but just be careful, okay? So if I say this minus this as the difference, then here this would mean D is what? Less than 0 or bigger than 0? Yeah, if you subtract x2 both sides, then if you subtract x2 both sides, that this is what you get, which is D greater than 0, right? So if you define it like that, then it's a right-tailed test. If you define the opposite way, x2 minus x1, then that would mean that the alternative is D less than 0, so you end up having the left-tailed test, okay? All right, So you have a right tail test, and let's again use alpha as 0.05, and we need to do an inverse norm, and you have 0.95 with the standard normal distribution. Can somebody give that to me? It's 1.6445, is it?
Yeah, it's 6,448.
8, okay. Oh, 645. So that's our critical. That's going to be step 2. Okay, now step 3. You're thinking of comparing the difference, and the actual difference that we got. Oh, there's something that's not right here. Yeah, I should really say mu1, mu2, mu1, mu2. Okay, then this should really be mu1. Sorry about that. Yeah, the previous one should also be corrected. Yeah, the reason is here, of course, x1 is bigger than x2 bar, right? Of course. That's not what we're talking about. What we want to know is if we took all the athletes and then compared with all the non-athletes in that college, which will take more time, okay, or maybe it might not even be possible, who knows, then can we still talk about it if you talk about the same thing, even if we looked at the population? Okay? So the hypothesis is on the population means, not the individual sample. We already know that for the sample mean this is bigger than that one. Okay? You see the difference? So when you do the hypothesis testing, you should always write down the population mean or population proportion. So for means, you should always use mu, not x. Okay? Yeah, sorry about that. You should go back to your notes, and for the first one, you should change that x1 bar equals to x2 bar. That should be changed to mu1 and mu2. Okay? So please change that. All right. So step 3. Now your test statistic is the actual difference that we know. So what is D here? D from the sample here is 2.91 minus 2.81, which is 0.1. Okay, so that's what we get for the top. Well, it's really 0.1 minus 0 because that's the assumption in the hypothesis. Divided by this value, 0.0467. All right, so can somebody calculate this for me? What is 0.1 divided by 0.0467? So
2.141.
Okay. Now, does this fall in the rejection region?
Yes.
Yes, it does. So what's your conclusion?
We reject the null hypothesis.
We reject, so this is in rejection region. You have to write that somewhere. It's better to put it here. So since the test statistic falls in the rejection region, we reject the null. And the data shows the average or GPA of average GPA of athletes is higher than average GPA of non-athletes with 0.05 significance. or added, right, at 0.05 significance. So the data shows that the average GPA of the athletes is higher than the average GPA of the non-athletes at 0.05 significance. Okay, so let's think about this question. I guess acute hip fracture means that you had an accident. You fell down the stairs, or you fell walking somewhere, and you have a hip fracture. And not all places in America have good hospital systems like in Europe. So you might have to go to that one hospital which is like many hours away, and then even if you go there, the doctors might not be available to see you, so some people might end up getting the surgery more than 48 hours. So I guess the 48 hours is something like a standard. And for some healthcare researchers, this could be an important question. Like, if you have an acute hip fracture, how important is getting the surgery within time? So they would look at some large data of people who had surgery, and I guess many of them had a 3-month follow-up, and they were asked to walk. Can you walk without assistance, or do you still need crutches or whatever? Okay. So they're doing that, and it turns out that 13,122 patients among the 16,200 who received the surgery within 48 hours could walk after 3 months, which is good. And for the other group who had their surgery past the 48 hours window, 9,709 patients were able to walk among the 13,300 who had the surgery past the 48 hours. So now the question is, can you say that there's a difference between, so test the hypothesis that those who get the surgery within 48 hours have better chance of walking. Which is a reasonable question to ask, right? And I'm saying that the key to solving these hypothesis testing is to first identify what type of problem it is. If you don't know the exact type, then you end up using the wrong formula and you end up with the wrong conclusion. Okay? So what type of hypothesis testing is this?
Two proportions.
It's a test of two proportions. Okay? So this is a hypothesis testing of two proportions. Okay? And for such case, you need to, so one thing that you have to remember about testing two proportions, if it's a hypothesis testing of two proportions, you have to at some point calculate the pooled proportion. I'll call that p hat. Okay? So there are actually three proportions here. So first, P1 hat is the proportion from the first one, which is 13,122 divided by 16,200. Help, please. Anyone with the calculator?
0.81.
0.81, thank you. And P2 hat would be 9,709 divided by 13,300, which is
0.73.
0.73, thank you. And then how do you get the pooled proportion?
Add them both together, the two populations.
Add the numerator and add the denominator. So you're thinking of the two populations as if they actually is a sample from the same thing. You don't treat them as different pools of data. You just pool them together. That's why it's called pooled proportion. So you do 13,122 plus 9,707 and divide it by 16,200 plus 13,300. So what is this? Yes?
We're 9709.
Oh, thank you. 9,700. All right. So what's the pooled proportion?
0.77.
0.77. Okay. All right. So that's what it is. Now let's start with the four-step procedure. So step 1. The null hypothesis is that what?
P1 equals P2.
P1 is equal to P2. So for the proportion, I'm using the hat to be denoting that it's a number from the sample. And if it's not from the hat, if it doesn't have the hat, these are the proportions from the population. Okay, so this is okay. Now some textbooks go by this strict rule that anytime you're talking about the population, you should be using the Greek letters. And the thing is, what's the Greek letter for P? Do you know what it is?
Pi.
Pi, yeah. So some books you're going to see pi 1 equals to pi 2. Yeah, I guess that's all right, but you know, it doesn't look so nice because we tend to think of pi as 3.14. Well, some books do that. I just don't like using that one, so we're just going to use this one. Okay, so H0 is that the two proportions are the same. The alternative hypothesis is that they're different. Actually, we want to show that P1 is greater than P2. So it will be, if I use the difference to be P1 minus P2, this would be right tail test. So step 2, the rejection region would be the right tail with 5% all here, so inverse norm of 0.95, 0 and 1, that's going to give you 1.645. And then step 3, you have to calculate the test statistic. So the test statistic, Z, is equal to the difference between the two, so P1 minus P2, which is 0.81 minus 0.73, divided by square root of P hat Q hat over N, right? Okay? So that's when you use the pooled one. So for the standard deviation, that's what you use. All right, and just remember that
Q hat's 1 minus P hat.
yeah, Q hat is 1 minus P hat. So this is 0.08 divided by 0.77 times 0.23 divided by, and this N should be the pooled one, so you have to add the two. And the reason that you do it that way is because when you're doing hypothesis testing, you're operating under the assumption of the hypothesis. I don't know, I can't pronounce that one. So you're operating under the hypothesis. So that means you're thinking of the two things as one gigantic sample, and therefore that's your N, okay? So what are we using here? 295 okay. So, what do you get? Can somebody tell me the answer? What do you get? Square root of the entire thing.
$32.65.
That high?
Yeah.
Wow.
I got that too.
Okay. Yeah, that's really high. It's way, way over this. So there's no question about it. Like, for these numbers to be produced just by chance, no way. So step 4, we reject the null and conclude that yes, indeed, having the surgery within 48 hours increases your chance of walking a lot more. There's a significant difference between the proportions from the 48 hours, within 48 hours group and past 48 hours group. Okay? So I'm not going to write them all, but you should write them and be able to explain what the conclusion is, right? That's all.